All right, thank you all very much for coming along. My name's Ian Robinson. I'm an engineer with Neo. I'm based in London. And for the last 18 months or so, I've been working with a team there, building out some of the infrastructure that we use for testing Neo. And so, in fact, over the last few weeks, in preparation for 2.3, we've had more than 200, up to 300 instances running in AWS testing Neo and tested clustered versions of Neo over very long periods of time, many days and many weeks. What we're going to be talking about today is deploying your application, moving your application, your Neo4j-based application into production. And I'm going to be talking about some of the things that you want to think about early in the application development lifecycle, some of the deployment options. And I'm also going to be talking about some of the things that you need to think about when you're designing your environment, and also some of the operational activities that you'll want to perform once you've got that app into production. So these are all the different topics we're going to touch on over the course of the session. So thinking first about deployment options. You know, you want to build a Neo4j-based application. There are three different ways in which you can incorporate Neo4j into your app. You can use embedded Neo4j, you can use the server version of the product, or you can use the server together with Unmanaged Extensions. So this first one, embedded Neo4j. I think Emil hinted at this or talked about this briefly in his keynote this morning. Neo4j started life as an embedded graph database. Okay? Effectively started life as a library that you hosted in your own Java process, in your application's Java process. And you can still do that today. You can treat Neo4j as a library that makes its data durable on disk. And your application can speak to Neo by way of a rich set of Java APIs that allow you to talk in terms of those primitives, nodes, relationships, properties, and labels. And you also have access to a couple of other APIs, the traversal framework, to our graph algorithms package, and so on. So that's one way of incorporating Neo into your application, treating it as a library and using embedded Neo4j. The more common version today is to use the server version of the product. Effectively, we've built the server infrastructure that surrounds an embedded graph database instance. So you spin up a server. This is our typical experience of a database. We want our databases to be somewhere else on the network. We'll have a client driver, and we just expect to be able to speak to that database, talk to the database over the network using that client driver. And that's effectively what you get with the server version of the product. Okay? So it's a server infrastructure that embeds or wraps an embedded graph database instance. So there's still an embedded graph database in the background there or at the heart of that server. And then we expose an HTTP API, a set of REST APIs effectively that allow you to communicate with the server. And this includes a transactional endpoint that allows you, from the client side, to control the scope of a transaction, to start a transaction, submit multiple queries in the context of that transaction, and then finally close it. Okay. So this is a typical architecture here where we've got our application code, the stuff that's specific to your domain, to your application, a driver as part of that, and typically it's talking by way of a load balancer to a Neo4j cluster of server instances. Okay. And then the third deployment option is to use the server version of the product, but to extend it using what we call unmanaged extensions. So for a long time, we've given you the ability to be able to write additional pieces of code, Java code, and to sit them inside of the server. These are unmanaged extensions. Okay? And these extensions have direct access to the embedded graph database that is at the heart of that server. So from within your unmanaged extension, you can use all of those lower-level Java APIs or the graph algorithm package or the traversal framework in order to talk to the embedded graph database. And then you expose your functionality, your extension's functionality, by way of another REST API, a set of URIs. So you can think of it as being a cheap way of doing stored procedures, locating some code inside of each server, and then, again, using a client, perhaps a Jersey client or something like that, being able to communicate with those extensions. And the advantages here are you're still in a network environment, you're still dealing with the server version of the product, But your extensions themselves are a lot closer to the data. You can take advantage of those low-level APIs. But they also give you a lot of control over the request and the response format. So you can actually create request and response formats that are more sympathetic to your domain. Instead, perhaps, of talking in terms of nodes, relationships, properties, and labels, you may want to talk in terms of products or users and so on. Okay? So these are our 3 different deployment options. And this is a choice that you'll probably make early in your application development lifecycle. The most common deployments today are either the vanilla server version of Neo4j or quite often server together with unmanaged extensions. And again, as Emil mentioned, or perhaps Philip mentioned this morning, when talking about the universal language drivers, any investments that you make in unmanaged extensions today, you'll be able to port very easily to 3.0 and to those universal language drivers, because effectively you'll be able to use the core logic that you develop in any extension and treat that as a store procedure that you can invoke using the Bolt protocol. So there's some of the upfront deployment options or decisions that you might have to make. Thinking then about actually moving an application that you have developed, having made one of these decisions, into production, we start thinking about those target environments. So I've got a couple of slides on hardware and software, and I'll just go through them quite quickly. Hardware, first of all, thinking about production hardware. Lots of cores and lots of RAM. Okay? You're going to perform best if you've got machines with lots of cores. Neo4j scales with the number of cores. If you're using the community version, it scales up to 4 cores. If you use enterprise, then it scales beyond that. Okay, so it scales for reads and writes with the number of cores. And then in terms of storage, ideally SSD rather than hard disk, and not the kind of commodity SSD, but this more specialized single-level cell SSDs are the kind of things that we recommend. Lots of RAM. Even though we're making all of that data durable on disk, you want lots of RAM because you want to be able to cache a lot of that data in memory. So again, stuff that came out of the keynote. We've invested very heavily over the last year and a half or so in the development of this off-heap page cache. Okay? And this is the thing that's going to give you a big performance benefit here. If you can assign lots and lots of RAM to that page cache, then you're going to improve the performance of many of your queries. So today, we kind of recommend that if you've got plenty of RAM, assign between about 8 and 12 gigs to the heap itself, and then assign lots and lots of the remainder to the page cache. Okay? So one thing that I always recommend is that you should explicitly set the size of your page cache using configuration, using this configuration option here, dbms pagecache.memory. And you should size this. If you've got enough RAM to cache the entirety of the store in RAM, then you should probably size this at the size of your entire store, plus 10%, plus some considerable headroom for growing that store over time. If you don't have enough RAM to map the entirety of the store into memory, remember to leave lots of room for the operating system itself and for any other processes that might be running on that box. So we're kind of assuming that you're dedicating machines to running Neo4j, but there are often other processes that you end up running there as well, monitoring or deployment processes. So you need to be able to leave some space for those as well. If you don't explicitly configure the page cache, then Neo4j will try and make some intelligent decisions. In versions prior to 2.3, if you didn't configure it explicitly, Neo4j would try and assign about 75% of the RAM that was left over once it had deducted the heap size. It would try and assign that to the page cache. In a lot of our testing, we discovered that can actually create some out-of-memory conditions when we're really thrashing this thing. So we've lowered that default value to about 50% in 2.3. So if you don't explicitly configure it, then Neo4j will configure it at 50% of whatever's left over once we subtract the heap size from the amount of available RAM. In terms of software, the JDK we recommend either OpenJDK or the Oracle Java 8 JDK today. If you are stepping up to use something like Power 8, then we qualify using the IBM JDK on Power 8. Okay? In versions of Neo4j prior to 2.3, the default garbage collector was the CMS collector, but we switched that now to using the G1 garbage collector. That's the default collector that we now use in 2.3. And what we found is that using the page cache with no object cache, and in 2.3 there is no object cache, but using the page cache plus the G1 garbage collector, we get far better throughput and far better stability than ever we saw in 2.2 and in previous versions of Neo4j. So even if you're on 2.2 today, it's worthwhile experimenting with the G1 garbage collector, removing the object cache, configuring the page cache, and switching to the G1 garbage collector. And I think you'll experience, firstly, improved throughput, but also increased stability there. So yeah, if you're on 2.2, there's the additional configuration that you need in order to be able to specify the G1 garbage collector. Okay. Lots of our users now are deploying Neo4j into different cloud environments. The one that I'm most familiar with is Amazon, so just to give you some hints as to the kind of things that you should be thinking about here if you're thinking of deploying Neo4j into the cloud. In AWS, we found that instances, so you've got choices around the instances themselves and then the storage volumes. We recommend choosing instances that HVM instances, these hardware virtual machine instances, they perform slightly better for our workloads than the older paravirtual instances. The volumes themselves should be using elastic block storage so that you can snapshot your stores. This is that kind of durable, snapshotable storage that AWS offer. So when you're choosing your instances, ideally you should either choose instances that are already EBS optimized, or you should provision them as EBS optimized. This effectively ensures that you've got dedicated throughput to those EBS volumes. So the instances that we use for a lot of our heavy soak testing are the R3 memory optimized instances. So something like R3X large, we get just under 31 gig of RAM, and that's 4 virtual CPUs. With some of our clusters, we go up to R3, I think 4X large, where we've got a lot more RAM and many more CPUs to play with. R3 isn't EBMS optimized by default, so we actually have to provision that when we're creating instances. Whereas C3, C4, these compute optimized instances, are effectively EBMS optimized by default. So they're some of the different instance types that we recommend when if you're choosing to deploy into AWS. Neo4j is a database and therefore is always going to be I/O heavy. So there's always going to be a lot of I/O work. So when you're choosing your volumes or provisioning your volumes, our recommendation is always to choose provisioned IOPS. This is effectively you being able to specify or reserve an amount of I/O capacity, and that leads to far better, far more predictable performance. So provisioned IOPS is really there for I/O-intensive workloads. And you can provision that, it's more costly, it's more expensive, but you can provision that at about 30 IOPS per gigabyte. So if you have with a ratio of 30 to 1, so if you have, for example, a 300 gigabyte volume, EBS volume, then you can provision that at about 9,000, maximum of 9,000 IOPS, okay, I/O operations per second. You will, under very, very high throughput scenarios, you probably will end up maxing out those IOPS. So, you need to perhaps increase the size of the volume and therefore provision more IOPS. But this is stuff that is always worthwhile monitoring. Okay. So that's just a brief tour around some of the hardware and the software decisions that you need to make when you're thinking about those production environment options. Okay. HA architecture. So unless you're building a desktop app or you're building a small, lightly trafficked, non-critical web app, you're going to want to be using Neo4j in its clustered form. Okay, so we can cluster Neo4j instances for high read throughput and high availability. And this is a feature of the enterprise version of the product. So Neo4j today employs a rather traditional master-slave architecture. Here we've got a cluster of 3 instances, and at any one point in time, one of those instances will be acting in the role of the master. And the master is responsible for coordinating all of the writes to the system. And then the other instances in the cluster act as slaves. And they're polling the master at frequent intervals in order to pull transactions across. Okay. So effectively, we have 2 different protocols going on here. We have a Paxos-based cluster management protocol responsible for deciding who's the master at any one point in time. And then we have a separate transaction propagation protocol, which is effectively the slaves pulling transactions from the master. As I say, the master's responsible for coordinating all of the writes to the system. So if you write directly to the master, when the control returns to the client, you're guaranteed your data has been made durable on disk, and the master is immediately consistent with respect to that client. The overall system, however, is eventually consistent in the order of several milliseconds. Whatever the polling interval for those slaves is, effectively we're going to propagate transactions in the course of that polling interval. So the overall system will be eventually consistent in the order of several milliseconds. Okay, so we choose HA for high availability and high read throughput. Just a few things to be aware of when you're configuring your clusters. There's a lot of different configuration options, a lot of stuff that's explained very well in the manual, but just a few things that I wanted to point out here. The first thing is something that we call initial hosts. So there's a configuration option called initial hosts. Whenever you introduce a new instance into a cluster, we need to supply it with the address of at least one other instance in the cluster that is currently up and running, so that it can contact that instance and discover the rest of the cluster. So this is this HA initial hosts value. You can configure it with just one other address in the cluster, or you can configure it with a list of addresses. But the important point is, when that instance starts up, all of the addresses that are in that initial hosts value, all of those instances have to be up and running and contactable at that point in time. So if you've got a very large cluster and you're introducing a new instance into it, you probably don't want to list all of the currently running instances. Probably just limit it to 1, 2, or 3 other host addresses. The next set of options, pull and push transactions. So I said that with our transaction propagation protocol, effectively the slaves are pulling transactions from the master. You configure that with this HA pull interval. Now, for some reason that I've forgotten or I've never chosen to investigate, that is actually off by default. So if you configure a cluster without specifying this pull interval, then the slaves will never bother contacting the master. It'll all hum along very happily, but there'll be no data being propagated around. So you should configure this HA pull interval. I've configured it here. Every 10 seconds, this particular instance is going to contact the master and pull data across. We also have this TX push factor, which we introduced quite a while ago, which is a kind of best efforts attempt on behalf of the master to push transactions out to the slaves, to one or more slaves, at the point when we're writing to the master. This is on by default, and it's on with an initial value of 1. So whenever we write to the master will try and contact one other instance in the cluster and push that transaction across at that point in time. This is not the most thoroughly robust way of ensuring that those transactions are propagated, however, because this is best efforts only, and will not signal back to the client the fact that we perhaps couldn't contact other instances at that point in time. So you should always be specifying the pull interval, but the push factor actually gives you the option to push data out more quickly than the pull interval would allow. And then there's a whole slew of tuning options, all of this stuff described in great detail in the manual. The things that I've pointed out here probably the most important is this heartbeat timeout. So all of the instances are sending heartbeats. By default, they're sending heartbeats every 5 seconds. And then there's a heartbeat timeout value, which we recommend you always configure at twice the heartbeat value plus a little extra. So if we're sending heartbeats every 5 seconds, the default value for the timeout is 11 seconds. If an instance doesn't hear a heartbeat from some other member that it believes should be sending a heartbeat after 11 seconds, then it starts suspecting that member. And if that member that it's suspecting is the master, then this can potentially trigger a master re-election. So, if you find that you're suffering master re-elections, and you see in messages.log that some of these heartbeats are being sent after 5 seconds or outside of that 11-second interval, then you might consider increasing that value. The downside is if a machine really does go offline, you're going to find out about it a lot later. With this particular setting, we're going to find out that the machine is genuinely not available after 11 seconds. If we increase that value, that's going to extend that window. All right, so we're using clustered Neo4j. We've talked about some of the options there for configuring it. So now we've got our cluster up and running. We can then begin to interrogate the cluster to discover at any point in time who's currently the master and who are the slaves. So each instance that's running, if we're using the server version of the product, exposes these 3 different HA endpoints. DB manage server HA/master/slave and /available. And we can issue an HTTP GET request against each of these endpoints in order to discover, are you the master, are you a slave, are you simply available? And this is very, very useful, particularly if we're configuring a load balancer so that we want to route, and I'll come on to this in a bit more detail, but if we want to route writes directly to the master and we want to round robin read requests across the entire cluster, then we need to be polling each of the instances probably every couple of seconds to discover and to remind ourselves who's the master. Okay? And then I've just listed here the HTTP status codes that each of these would return, depending upon the state of that instance, and actually the body. There's a simple text body that's included with every response as well. So depending upon the way in which you might configure your load balancer or any other application code that wants to use this, you can either use the status code or the entity body to infer the state of that particular instance. Okay. Now, in 2.2, if we secured Neo4j, if we required authentication for Neo4j, then we also required authentication for these endpoints. And that's a good and proper thing to be requiring, perhaps. But at the same time, it's there's a slight operational hurdle to overcome here, and we end up having to configure our load balancers to authenticate against these endpoints as well. So in 2.3, there's an additional little configuration property here that allows us to switch off the authentication just for these HA endpoints. Everything else will still be secured, but these HA endpoints we can contact without having to supply credentials. Okay. And we included that based on feedback from customers and users who preferred the simplicity of this model without having to configure their load balancers with credentials. We can also discover some additional information about each instance using JMX. So Neo4j exposes a lot of internal counters, a lot of internal state via JMX. But we actually also expose some of that JMX information at some URIs. So there are some URIs by way of which we can also gain some of that JMX information. The most important one is this one here. I'm not even going to begin to read it out. But if you grab the slides at the end of when they're made available, you'll be able to read this off. If we issue a GET request against this URI, then we'll get back a JSON document that describes this particular instance's view of itself and its view of the rest of the cluster. Okay? So the kind of information that will be included here is, am I alive? What particular role am I fulfilling at this point in time? Am I a master? Am I a slave? And then these 2 other pieces of information here. The last committed transaction ID for this particular instance, and also this particular instance's view of the rest of the cluster. And these 2 things are really, really useful when we're we're building monitoring tools, and we're wanting to understand the state of our cluster. So the first thing here, the last committed transaction ID. So I said we've got all of the slaves pulling transactions from the master. The master's coordinating all the writes, so therefore the master is responsible for assigning all of those transaction IDs. If we're in a very high throughput scenario, there may be situations in which some of the slaves begin to drift a little behind the master in terms of catching up. And we can identify that by polling each of the instances in the cluster and comparing the last committed transaction IDs. And if we see those, the delta beginning to increase over time, then we can infer that one of those slaves or some of those instances are beginning to fall behind in their catch-up strategy. We can then use this other piece of information in the JSON document to further reinforce our view of, is the cluster stable and healthy? So if we poll all of the instances and they all agree that there's one master and two slaves, and we see that in this additional information, then we can be doubly reassured that we've got a nice, healthy, stable cluster. Okay. So this HA JMX endpoint that we expose at the end of a URI, it's not very well known, but it's actually a very, very useful piece of additional monitoring information that we supply to you. Okay. Now, we can create cross-data center clusters, and very many people are doing this. Mainly for failover purposes, but occasionally in order to, if they've got a globally available application, they often want to have secondary parts of the cluster located close to some of the consumers elsewhere on the planet. So if you're building a cross-data center cluster, our recommendation, ideally use a VPN. We need to be on the same subnet. We need to ensure that the bandwidth between those data centers is aligned with the right throughput, both if we're pushing transactions out from the master, but all of that transaction propagation that the slaves are going to require when they're contacting the master. So we need to provision that bandwidth to ensure that we can actually get this data pretty fast between physical locations. We could have a cluster that spans multiple DCs where if there's a master re-election, the master could hop from one data center to the other. But very often that's not actually what you want. What you really want is you'll have a primary data center where the core of your application is located, and where, if there ever is a master re-election, you want to guarantee that it takes place within that data center. And then your other data centers, your secondary data centers, are effectively slave-only instances. They're still all part of the same cluster, but they're slave-only instances. And we can configure that. The instances that are in that secondary data center, we can configure the slave-only property to be true, and those instances will only ever act in the role of a slave. And by setting this property, we effectively restrict master re-election to the instances in the primary. So once we've got our clustered Neo4j, we're effectively scaling out for high read throughput. And I said this is a typical application architecture where we've got the core of our own application code at the top here, and then we're talking to Neo4j using a client driver, but inserting a load balancer in between. Things like HA Proxy. In Amazon, we might use Elastic Load Balancer. We can use things like NGINX. More often, this is an equivalent architecture here where we've got a pair of load balancers. So we've got one load balancer or logical load balancer that is responsible for identifying the master, even if the master switches over time. And the application will send all of its write requests to the right load balancer, and it will forward them direct to the master. And then we have a second load balancer, which is responsible for servicing read requests. And that can either just load balance across the slaves, or it could actually round robin across the entire cluster. My colleague, Stefan Armbruster, has written a good blog post about how to configure HA Proxy for doing some of these things. So again, we don't really want to go through all of that configuration here in this session, but there's a great example in Stefan's post there of configuring HA Proxy for precisely these kinds of scenarios, identifying the master, routing writes to the master, and load balancing reads across the rest of the cluster. The advantage of using a load balancer is that we can employ a strategy called cache sharding. Okay. So this is incredibly useful when you have a very, very large store. And even though you may have a lot of RAM, potentially, with really large stores, you're never going to fit all of those stores into memory, into that page cache at any one point in time. So what we want to be able to do is to reliably route requests to instances in the cluster where those caches, that page cache, has been warmed with a portion of the graph that's relevant to that particular query. So effectively, we're using traditional kind of consistent routing techniques in the load balancer to ensure that requests are consistently routed to specific instances in the cluster. So if we've got a read request matching country Australia, we'll direct all of those countries beginning A to I will go to instance 1. Norway will go to instance 2, Zambia to instance 3. Australia, again, instance 1, Norway instance 2, Zambia instance 3, and so on. So we're consistently routing requests to specific instances in the cluster where that page cache has been warmed or gradually warms up over time with portions of the graph that are relevant to that particular part of the domain. So we need to often choose some domain-specific information or insert something into a header that will help us do that consistent routing. But this effectively provides for, again, a very effective use of clustered Neo4j for servicing a very high read throughput scenario with a very large data store. Okay. So that's the use of clustered Neo4j and some of the strategies that we can employ when we're using Neo4j HA. Now I'm going to talk about some of the operational activities that we're going to want to do moving our apps into production. The first is backups. So Enterprise Neo4j supports online backups, so you can back up a running instance without having to stop it, take it down, or anything like that. And there are two kinds of backup. You can do a full backup, and then having got a full backup, you can do a series of incremental backups. Okay, so you'll do an incremental backup based upon some previous backup. Okay? In order to be able to do an incremental backup, we need access to all of the logical logs that have been created since the last backup took place. So typically, we need to configure keeping those logical logs around for up to twice the backup interval. If we're doing incremental backups every 2 hours, then we need to keep those logical logs for at least 4 hours. By default, we're actually keeping logical logs for 7 days. But if you've got a very high write throughput scenario, then it may be we end up generating gigabytes of logical logs, and you might want to dial that down a bit. Okay? But you need to ensure that you've got sufficient logical logs in order to be able to do an incremental backup at any point in time. Included with the backup tool is another tool called the consistency check tool that by default will run every time you do a backup. And it's there just to check the health of the store, to check the health of the backup that it's created. Okay? We also expose this, we expose this consistency check tool also as a standalone tool. So you can either run it as part of a backup or as a standalone against a previous backup. Okay? So it's there effectively to evaluate the store health. Doing a consistency check can take quite a while. If you've got a really big store, then you're looking at many hours, tens of hours, even perhaps a couple of days for several hundred gigabytes of store. So it may be that you don't want to consistency check every single backup, and in that case you can supply a kind of verify false flag just to do the backup and not to do the consistency check, not to do the health check. Backup strategies, there's nothing surprising here. You could do a local backup on the instance where the database is running. But we tend to recommend that you do a remote backup. Introduce another machine into your environment, and then you just need the backup tool on that machine. You don't need a running instance of Neo4j, you just need the backup tool. But that backup tool can do a remote backup from one of your instances in the cluster. Pull it over, and then if we're doing the consistency check, we're effectively doing the consistency check offline with respect to the database. So the hard work is actually pulling all the data across in the first place. But once that's done, the database just continues as normal, and we're left doing the consistency check on this separate machine. If you've got a large cluster, it may be that you assign one of those instances to be a dedicated backup slave, so we're always targeting that particular instance for our backups. An alternative strategy is effectively to round robin. Each time we do a new backup, we'll pick another instance in the cluster. So we're kind of spreading the load over time. To restore from backup, it's very, very simple. A backup is a full copy of the store. So if you need to ever restore from a backup, you stop a particular instance, you remove the old version of the store, you delete the graph.db directory, and then you replace it with the backup and restart the instance. And that's all that you have to do in order to be able to restart from the backup. In the kind of long-running soak tests that we do, typically we have clusters of 3 or 5 instances. We have a separate machine elsewhere in our environment, so we're always doing remote backups. And we tend to round robin across those instances, and we also tend to do a full backup followed by 5 incremental backups. So I'll do a full backup against A, an hour later perhaps a full backup of B, a full backup of C, and then when I go back to A again, I'll do an incremental. And I'll do that over and over until I've done 5 incremental backups of A, and then I'll do a full one again. Okay? And we're always just effectively keeping a note of what was the last successful backup that we've done, because that's effectively the one that we would use to seed a new instance in the cluster, or if necessary, to restore an instance in the cluster. So that's backups. Monitoring. No, the question is graph.db one huge file? No, it's not. There are several different stores on file. Several different stores on disk. Each store is its own file. So there's one for nodes, one for relationships, one for properties, and so on. There's about 10 or 12. We don't run into operating system limits with regard to the number of files. Something that I've not pointed out on these slides, but if you're running on Linux, we always recommend you increase the number of file handles that you can have. Because by default, it's a really tiny number. It's like 1,024. We use Lucene as our index provider. And when Lucene is running and you're doing lots of writes, Lucene generates lots and lots of small intermediary files that it then begins to group together. So the number of open file handles that Lucene generates can quickly go into the tens of thousands. So we recommend that on Unix, you up that U limit to about 40,000 or so at a minimum. Yeah, good question.
Just a quick question on backups. Do you have a concept of recovering from a commit?
So the question is, do we have a concept of recovering from effectively point in time or from commit? At the moment, no, we don't. So although we have incremental backups, we can't dial back in time. So I've just got a couple of minutes left. Let me talk very briefly about monitoring. For years, we've exposed all of those JMX counters, but in 2.3, we've now started exposing additional counters that we can push, or that the database can publish. Today, we support publishing to Graphite, Ganglia, and to CSV files. Okay? And the kind of information that we're capturing are things about the node counts or the entity counts, about the HA network usage, the different kinds of transactions that are running or have been committed, the behavior of the page cache, and then some JVM-specific counters as well. In our soak testing, we use those metrics together with things like collectD to collect information about the system itself. We tail messages.log looking for errors and warnings. We use those HA endpoints to determine who's the master, who are the slaves. We look at the HTTP log to calculate the latencies on the server for each request. There are some additional slow cipher query logs that we can switch on. And then in our application itself, or in our load generator, we'll also have the client's view of the behavior of the system, the overall latencies as far as the client's concerned, and we bring all of that stuff together in something like Graphite. So we have an internal and an external view of the system at the same time. And we can often collate or correlate between the client started seeing some very, very large latencies here, or look at the behavior of the JVM over here, or the behavior of the page cache, and so on. This should not come as any surprise. When you're putting your app into production, beforehand, for a long time beforehand, you should be testing at scale. This is exactly what we're doing on your behalf, but we can't anticipate all of the different application architectures, all the different data sets, all the different kinds of queries. But as I say, over the last 6 weeks or so, we had up to 300 instances, often 30 or more clusters running in AWS for many, many days, doing all of this kind of stuff, running client workloads very, very aggressively, kind of maxing out the instances, doing lots of operational things such as backups, replacing instances, and doing some naughty stuff like killing instances and introducing partitions and stuff like that, just to be confident that this thing remains stable over a long period of time. But that's exactly what we'd expect you to be doing as well when you're putting this stuff into production. That's pretty much it. The end slides here, I've got some performance tips, but effectively, they're things like cipher tuning, which the previous session touched on, enabling GC logging if we're starting to see any pauses, if we want to understand the behavior of the garbage collector. Using unmanaged extensions where we've got very performance-critical things that perhaps today's cipher isn't working for us. We can use unmanaged extensions, confident that we'll be able to reuse those in 3.0 if we move up to 3.0. Your investment isn't wasted there. And that's pretty much it. I mean, that's taken me through 40 minutes, a very, very quick tour of putting stuff in production. I hope it's been useful. Find me afterwards, because I think we've run out of time for questions. I'm sorry, I've kind of filibustered to ensure that nobody can ask me anything. But find me and ask me, and I'll answer your questions.